Hi, we are going to discuss something called multiplicity of real zeros for polynomial functions. A reminder that a real zero of a function is a real value where the function is going to be 0. And we also know that as x-intercept. So we need to determine real zeros of these polynomials and their multiplicities. Here's what we need to know. First of all, if you set this whole thing equal to 0, you should see that x minus 3 equals 0. And x plus 2 equals 0, or x minus 4 squared equals 0. I'm going to keep this square here for a moment. So this gives us 3, this gives us negative 2. Each one of them has exponent 1, an implied exponent 1, which means the multiplicity here is going to be 1. And the multiplicity here is going to be 1 as well. The multiplicity here is going to be 2 because what this means, this is the same as saying x minus 4 times x minus 4. So a 0, x equals 4, that 0 is used twice, and that's what multiplicity essentially means. So when we write x equals 4, the multiplicity here is going to equal 2. All right, let's take a look at the next problem. Hopefully it will make more sense. So in this problem, x plus 1 times x minus 2 times x plus 5. You have cube here and square here, so you want x plus 1 cube to equal 0, which means you're going to get x equals negative 1. The multiplicity here will equal to that exponent, so the multiplicity here is going to equal 3. This second factor here, x minus 2 equals 0, means that x equals 2, and there's an implied exponent 1, which means the multiplicity is 1. And our last part here is x plus 5 squared equals 0, which we know means x equals negative 5. The multiplicity here is going to be this exponent, which means it's going to be 2. So essentially multiplicity is going to tell you how many times a particular 0 is used in the expression. So if you were to write it out without the exponents, you're going to have to write x plus 1 times x plus 1 times x plus 1 times x minus 2 times x plus 5 times x plus 5. This would be the same as this polynomial here, and you see that x plus 1 is used 3 times, so multiplicity is 3. X minus 1 just once, multiplicity is 1, and x plus 5 we use twice, so multiplicity is 2. Okay. Let's try to do the same thing here. We're trying to find zeros and their multiplicities. We're not doing anything different now. You go on 2x minus 3 equals 0, which means x equals 3 halves. Only once the multiplicity is going to be 1. 5x minus 2 plus 2, to the 4th equals 0, which means you want 5x plus 2 equals 0, gives you x equals negative 2/5. The multiplicity here is going to equal 4, because we have an exponent 4. And x minus 1 cube equals 0, means x minus 1 equals 0, means x equals 1, and this one's going to have multiplicity of 3. One more example. So we have 4 different parentheses here. So 2x plus 5 equals 0, means x equals negative 5 halves. The degree is 1, the multiplicity is 1. X plus 1 cubed equals 0, meaning x equals negative 1. The degree is 3, the multiplicity is 3. X minus 2 squared equals 0, which means x equals 2. The multiplicity is going to be based on this exponent, which is 2. And lastly, x minus 1 equals 0, x equals 1. There is an exponent of 1 here, so its multiplicity is 1. Okay. So how do we recognize different multiplicities based on the graph? When you have a multiplicity of 0, we call it a single 0. The graph simply cuts through the x-axis. If you have 0 with multiplicity 2, it's always going to be a situation in which the curve is going to bounce off the x-axis, either from the top or from the bottom. Any multiplicity that goes, that's 3, or possibly 5 or 7, any odd multiplicity above 1, is going to have this type of behavior. When the graph is going to be rising, then it kind of flattens for a brief moment and continues to rise, or vice versa. So this is what the different multiplicities show up like on the graph. So what we want to do with these problems is we want to try to figure out this each 0 and its multiplicity. So obviously we identify zeros by looking at the points where the graph crosses the x-axis. So we have 1 point here, 1 point here, and 1 point here. So one of them is going to be -3. -3, the graph simply cuts through the graph. So that means multiplicity here for sure is going to be 1. Our next point is 2. So at 2, it bounces off the x-axis. Multiplicity has to be at least 2. And we also have x equals 5. It does the same thing as it does at -3, which means the multiplicity here is going to be 1. Okay, let's take a look at a couple more examples. So we have this problem. We also have 3 values, -1, 2, and 4. So what's going on at -1? At -1, the graph is going to bounce off the x-axis. That means the multiplicity will be 2. At 2, the graph rises, flattens, rises. So at x equals 2, that means multiplicity is going to equal 3. At least 3, possibly 5. And finally at x equals 4, the graph cuts through the x-axis. That means multiplicity here is going to be 1. Okay. And our last example here, we are going to have only 2 points. So x equals 2 and x equals 4. So at 2, the graph bounces. That means multiplicity here has to be at least 2. Over here it rises, flattens, rises. That means multiplicity has to be at least 3. Okay. By the way, a quick mention about multiplicity as far as the function behavior. If you add 2 plus 3 together, you get 5, which means this has to be possibly a 5th degree function. So at least we know it's an odd degree function. Both ends go in the opposite direction. It is consistent. Okay, and I hope this helps.